years later that if axions exist, they could make up the dark matter. And it's really today that the experimental effort for axions is getting into full swing. So throughout this talk, I'm going to walk you through this timeline. And as we go, I'm going to tell you about recent exciting progress that's been happening. So first, I need to explain to you the motivation for the axion. This is called the strong CP problem, but I'm going to call it the neutron electric dipole moment puzzle. And to start by explaining that, let me tell you the water electric dipole moment knot puzzle. So this is water. Water has an electric dipole moment because it's charge neutral, but there's a charge asymmetry. So what does this mean? You put water in an electric field and it precesses. Great. Let's try to estimate the magnitude of the electric dipole moment of water. There's a charge of about 1 electric charge separated over a distance of about 0.1 nanometers. So we'll estimate 10 to the minus 8 e-centimeters. Let's compare that to data, and we're off by a factor of 2. Pretty good. Let's zoom in at our nucleus. We have protons and neutrons. I'm going to focus on the neutron because it's also charge neutral, just like water. And naively, it looks like water, composed of quarks, up quarks and down quarks. And so what would I expect? I would expect an electric dipole moment, which points in the direction of that charge asymmetry. And this would cause my neutron to precess in the presence of electric fields. More concretely, there's a fundamental parameter of nature called theta. And a fundamental parameter of nature is like the electron mass. It's just some property of our universe. It is a number which is chosen for us, and it is what it is. And this number controls the magnitude of this electric dipole moment. If this parameter is non-zero, which is generic, the neutron precesses. If it happens to be exactly 0, the neutron doesn't precess. So let's try to estimate the magnitude of this electric dipole moment. The neutron is about 1 femtometer wide, and it has a charge asymmetry of 1 electric charge, so we'd estimate 10 to the minus 13 e-centimeters. If you actually do the calculation, you find this fundamental parameter of nature enters, but you get a similar number. But no neutron EDM has been observed. And the limit is 10 orders of magnitude smaller than the calculation. And that's confusing. And that's the strong CP problem. So more concretely, this puts a limit on this theta parameter. It turns out you should think of theta as an angle. You can kind of think of it as an asymmetry angle within the neutron. So it takes values from minus pi to pi, and we happen to live 1 part in 10 billion away from 0. So why? That's strange. Because if I am able to create a universe, I'll create a universe. I draw a value of theta, it lands over here. I need to do it again, it's over here. If I want to get this ball in that orange band, I need to do this at least 10 billion times on average. So it seems like something is fine-tuned. Fine-tuning problems are great because they often are hints that there's something dynamical going on behind the scenes. And that's what Petchy, Quinn, Weinberg, and Wilczek realized in the late, or proposed in the late 1970s, when they noticed the following observation. When I randomly create my universe, the neutron really wants to push theta down to 0. The neutron would be in a lower energy field configuration if theta could go down to 0, but it can't. Just as much as the electron mass can't evolve. It's just a parameter. So what they did was they promoted it to a dynamical object, to a dynamical field, the axion, and now the axion can minimize its potential. And at the minimum of its potential, there is no neutron electric dipole moment. So the picture which emerges from the late 1970s is that perhaps inside of the neutron, there isn't just quarks and gluons, but there's also these axion particles. And their job is to prevent the neutron from having an electric dipole moment by minimizing the energy of the neutron. So I'm about to start talking a little bit about cosmology and energy scales. So let me take a moment to step back and review very briefly the early universe. So what happened in the early universe? We had the Big Bang. We went through a period of inflation, which is a period of exponential expansion of space. Then that ended and the universe became a hot plasma, which then just cooled down as the universe expanded. That happened until we got to the QCD phase transition at a temperature of about a GeV, where quarks and gluons come together to form things like protons and neutrons. The next epoch we get to is that of Big Bang nucleosynthesis, where protons and neutrons come together to form light elements like deuterium and helium-3. And then we have the cosmic microwave background decoupling a little bit below an EV, giving us today beautiful pictures like this. Okay, that's cosmology. So I'm going to add one additional line here, which I'm going to add a line when the axion is born. And I'll tell you more what I mean by the axion is born. But the axion is born also through a phase transition, similar to this strong nuclear force phase transition. But this is expected to happen at a very high scale, scales 10 to the 10 GeV or even higher. So with that said, I'm now going to describe the strong CP problem a little bit more precisely. But if you don't follow this slide, that's fine, because starting on the next slide, we're going to go back to a pictorial understanding of the strong CP problem. But just to get everyone on the same page, in case you're wondering, I'm going to describe things a little bit more precisely here. So more precisely, the strong CP problem relates to this term, which could have appeared in the Lagrangian for QCD. You have that theta parameter, and G here is the field strength for the strong nuclear force. This generates an electric dipole moment, as I mentioned to you already. So the axion solution to the strong CP, as I mentioned, is to promote this parameter to a dynamical field, which is I'm going to call A throughout this talk. That field is born at some high temperature, which I'll denote by FA. I'm going to call this the decay constant or the PQ scale after Pesce and Quen, who are the people who proposed this. And that could be some very high scale, like 10 to the 10 or even as high as 10 to the 16 GeV. So in the cosmological picture, which is what I'm drawing here, as the universe expands and cools down, at this temperature, the axion is born. When we get to the QCD phase transition, the QCD confines, it generates a potential for the axion. Now, when the axion minimizes this potential, it removes dynamically the electric dipole moment of the neutron. This is the same picture that I sketched to you before. I'm just describing it a little bit more precisely. So what does this mean? Well, it turns out this coupling of the axion to the strong nuclear force also generates the coupling of the axion to electromagnetism, which looks like AE dot B, where E is the electric field and B is the magnetic field. And this allows the following important process to take place, which I'll reference throughout this talk. Axions can come in, hit magnetic fields, for example, in my laboratory, and convert into electromagnetic radiation, for example, into photons. The fact that the axion has a potential generates a small mass for this axion particle. That mass is inversely proportional to this high scale. So putting in 10 to the 16 GeV, I get a mass of around a nano eV. And the fact that the axion also has a mass will be important in this talk too. If you're a neutrino person, you might recognize this formula because this is the same formula that you find in the seesaw mechanism for generating the observed neutrino masses. So the seesaw mechanism involves a mixing of the active neutrinos with stereoneutrinos, where the stereoneutrinos have a mass which is very heavy, for example, at the scale of grand unification, 10 to the 15 GeV, which mixes with the electroweak scale to drive the observed neutrino masses, 0.01 EV. And one fascinating possibility is that both the axion and the observed neutrino masses are coming from physics at the same high scale. The reason the mass of that is smaller is simply because it's the strong nuclear force scale in the numerator, whereas for the neutrinos, it's the electroweak scale, and QCD confines at a lower scale than the electroweak scale. Okay, so now let's back up again from the equations. I just threw a lot at you, and I threw in particular a bunch of energy scales. So let's just walk through the energy scales that we have in particle physics. So the smallest mass, non-zero mass particle that we know about is the neutrino. The neutrino, as I mentioned, has a mass, their masses are on the order of 10 to the minus 2 eV. Going up in mass, we have the electron and the proton with masses of around an MeV and a GeV. There's then a whole bunch of other particles, essentially, well, the entire standard model, going up until we get to the top quark, which is the heaviest known particle with a mass of about 173 GeV. Everything after that is speculative. That's the highest scale that we know about in nature at present with data. We expect that the forces of nature unify at a scale called the grand unification scale, which is where we expect the electroweak scale, the electroweak force, to unify with the strong nuclear force. So I'm going to be referring to this scale throughout this talk, the scale of grand unification, around 10 to the 16 GeV. But it's just speculative. We don't know if this scale actually exists or if anything interesting happens there. And then lastly, we expect these forces to unify with gravity at the Planck scale, which is where we expect that quantum gravity becomes important. So the axion is going to be born, is going to be generated by new physics that happens somewhere around the scale of grand unification. Even though it's generated by new physics here, it has a very small mass. And the reason it has a very small mass is because of symmetry. Symmetries play a key role in generating the axion, and I'll explain that in a little bit more detail. But first, let me say that also axions arise in string theory. So I motivated axions by saying that they can solve this problem for us, the strong CP problem, but it's also now known that they arise very generically in the context of string theory compactification, where they arise from symmetries when you go from the higher dimensional theory down to our four-dimensional world. In fact, one could make the statement that axions could be the only way to experimentally probe string theory compactifications if we're able to discover these particles. So how can physics at some ultra high energy scale give rise to ultralight particles? The answer is symmetry. Axions are what are called Goldstone bosons of spontaneous symmetry breaking. And the way this works is the following. Let's imagine that I have a theory of a complex scalar field. So I have the magnitude, which is a real scalar field, I'll denote it by R, and a phase, which I'll denote by A. And that phase is going to be the axion field. And let me suppose it has this potential. If you plot the potential, you find the form shown here. So we all know what things like to do in potentials. They like to go to the minima. So where's the minimum of this potential? It's a circle. There's a circle of degenerate vacua. And so what happens about the minimum of this potential? The radial mode, R, is heavy. It corresponds to fluctuations up the side of this potential. It requires a lot of energy to excite it. But the axion is massless. It requires no energy to excite it. I just push it around the circle and it keeps on going. So the axion remains massless because of the symmetry of this potential. The symmetries play a deep role in protecting the mass of the axion and keeping it light. That's all I want to say about axions as a particle. I now want to move on and talk about axions as a dark matter candidate, but the lessons that we learned here will play a crucial role as we go through. So it turns out that we use very different language when we talk about axions as dark matter versus when we talk, for example, about WIMPs as dark matter. And the reason is that axions have a very small mass. So what does this mean? What we measure in astrophysics is the amount of mass within some fixed volume. So as we make the masses of the particles smaller and smaller, we need more and more particles to make up that fixed total mass. But axions are bosons. So as they pack together, eventually their quantum wave functions begin to overlap. We get high occupation numbers for each quantum state, and we transition from the quantum regime to the classical regime. So when we talk about axion dark matter, we use the language of classical field. Well, when we talk about WIMP dark matter, we use the language of particles, and it's simply because we're in a different regime of quantum mechanics. Okay, so I have this new classical field, and I need to include this classical field in the equations of motion for my universe as after the Big Bang. So these are the homogeneous equations of motion for the axion. Dots here are derivatives with respect to cosmic time. Ma is the mass of the particle, and h is the Hubble parameter, which describes the expansion of space. So this Hubble parameter is proportional to 1 over time. So as time goes on, this gets smaller, and temperature squared. So at very high temperatures, Hubble is bigger. Let's imagine we're at very high temperatures or early times. This term, the Hubble term, will dominate over this mass term. Then everything here has a time derivative. So if I forget about this last term, the solution is A equals a constant. So if I plot the solution to this, the axion field is constant. It's frozen at its initial value, called the initial misalignment angle, until Hubble becomes comparable to the mass. And then it just looks like a damped harmonic oscillator. It looks like locks on a spring, as we do in my intro lab. And it just oscillates and damps down. And after this point, the coherent fluctuations of this axion field behave like dark matter for astrophysical purposes. Making axions a good dark matter candidate, that doesn't mean you get the correct abundance of dark matter. To see if you get the correct abundance of dark matter, you actually have to carry out the calculation, and you'll find that you get the correct abundance of dark matter for an order 1 initial value of this axion field, assuming you have a decay constant on the order of 10 to the 12 GeV. But it turns out that that picture is only correct in one cosmological scenario. And that scenario is when the axion is born before inflation. So what happens here? So we're going down in time. Up. We're going forward in time, down in temperature as we go down here. So we go through the phase transition where the axion is born. And if I go from Hubble patch to Hubble patch, from one part of the universe to another at that epoch, the initial value of the axion field will change by some order 1 amount. But what inflation does is the rapid expansion of space-time. You can think of it as zooming us in such that afterwards we only see one initial value of the axion field. So in the subsequent evolution of the universe after inflation, there's only one initial value of the axion field. And it makes sense to use the equations of motion that I talked about on the previous slide. But the other possibility is that the axion is generated after inflation. Then I have these different initial values of the axion field, but through the subsequent expansion of the universe, they all come in contact with each other, such that my universe today, my visible universe today, includes in its history all of these different patches. So what am I supposed to do? Well, maybe you say I'm supposed to average over all possible initial values for the axion field. But that turns out to be a little bit too quick because I neglected gradients when I wrote down those equations of motion. Those play an important role here. I linearized the equations of motion. I shouldn't do that. I also, it turns out I developed topological defects, which play a very important role. So to make progress here, one has to do simulations. The equations of motion are too nonlinear to make progress, substantial progress analytically. And this is a big part of what my group does. We simulate this cosmology to try to make predictions for axions that we can hand over to experimentalists. And I want to tell you a little bit about some of these simulations we've run recently using resources just up the hill at NERSC, which is at LBL. So this is the theory we're simulating. It is that same potential which I showed you before. So we have our complex scalar field, which we're going to decompose into a heavy radial mode and our massless axion, or almost massless axion. So as I cool down in the simulation, I'm going to go through this phase transition, and I'm going to generate this potential, and I'm going to develop this massive radial mode and this massless axion. So what do I expect to happen as the universe expands and cools down? As the temperature becomes lower, I just won't have enough energy to excite this radial mode. So it'll freeze out and it'll become just not dynamical. But the axion is massless, so I can always excite it. It doesn't require any energy to excite that mode. So I expect to only have the axion dynamical, and the radial mode is just gone. And that's true everywhere except the locations of these topological defects called strings, axion strings. And at the strings, the radial mode is restored and it becomes dynamical. The strings are defined by the fact that if I go around in a circle around one of them, my axion acquires a 2 pi phase shift. If you think about shrinking a circle, you'll see that that's a singularity in the picture of only axions. And that singularity is resolved by the radial mode becoming dynamical, again, at the location of that string core. If that doesn't make sense, I'll show you some pictures where hopefully it starts to make a little bit more sense. But first, let me give you some intuition for why it's hard to do these simulations. These strings are very narrow. Physically, their width is smaller than the size of a proton, but they're very long. Physically, their length is cosmological scale, farther than the distance to the nearest star. We have to simulate something which is very thin and very long, and we have to hold that entire thing in memory in our computer, and that's hard. And that's why this is such a hard problem. This is not a string theory string. Yeah, good question. These strings are generated within the context of this particular theory. So the way that we make progress is we use something called adaptive mesh refinement. So what I'm showing you here is an actual string from one of our simulations. In yellow, you can see the string. The radial mode is shown in yellow. It's only turning on at the location of that string core. As the strings evolve, they emit radiation in the form of axions. It's that axion radiation which goes and determines the dark matter abundance. That's the thing that we care about. But to simulate this, we need to resolve the string over a very long length. And what we do is we use an adaptive grid, which can maintain high resolution around the cores of the string. but lower resolution elsewhere so that we can hold a bigger box in memory. And we can adapt the grid in real time to track the locations of these strings. So here's just another picture of it. This is done in collaboration with the computer science division, LBL. So we use code, which has different refinement levels. So our finest refinement level is just around the locations of the strings. And then elsewhere, we have a coarser refinement. And then we produce very pretty pictures like this, where you can see these strings coming around and emitting radiation in the form of axions. So I'm going to show you a simulation here. What I'm going to show you in this animation is just the strings. So keep track in the bottom left. You'll see a little box expanding. That's the size of the universe. So there it is right there. As the universe expands, you can see that these strings become dynamical and they start to wiggle around. They form loops. Loops contract. They straighten. They intersect. They're undergoing all of this complex dynamic. We actually don't care about that. What we care about is the axion radiation that the strings are producing, because that's what determines the dark matter abundance at the end of the day. So now let's zoom in on a sub box. It's a tiny part of this simulation. And what you'll see in blue is the radiation in the form of axions that these strings emit as they wiggle around. And it's that radiation and axion which goes on ultimately to set the abundance of dark matter in our universe. So I want to show you one additional picture animation of this, just because I think it's pretty. So this is a 2D projection where you can see these strings wiggling around, giving off shock waves of axions. The dynamics here is very nonlinear. And we count up all the axions that are produced, and we can then predict the dark matter abundance. So we put all of that together, and we get a prediction for the axion mass, which gives the correct abundance of dark matter. This is a very complicated plot, and I'm going to walk through it over the sequence of a few slides. But for the moment, just look at the x-axis. That's the mass of this particle, the mass of the axion, which gives the correct dark matter abundance. Or you can think about it in terms of the decay constant. Here, this is 1 over the decay constant on this axis. And what we predict is that the axion should have a mass between 40 to 180 micro eV in order to predict to have the correct abundance of dark matter, corresponding to decay constants on the order of 10 to the 11 GeV. And this prediction is useful because we can give it to our experimentalists who can then go and try to confirm or rule out this theory. So what are we doing now? We are running bigger simulations with increased dynamic range, better algorithms, doing more systematic studies with the goal of predicting the axion mass at 10% precision. Because at that level, it's a very concrete prediction that we can give to experimentalists who can rule out or confirm that this theory is actually realized in nature. So to summarize, if the axion is generated after inflation, the mass needs to be in this range in order to explain the dark matter abundance that's actually out there in our universe. If the axion is generated before inflation, essentially anything is possible here. This whole entire parameter space is possible, just depending on what the initial value of the axion field was that I happen to inflate from. In my opinion, in that case, the part that's very exciting is down here at smaller masses, because here the decay constants are on the order of the scale of grand unification, where we expect new physics to show up. So these two parts of the parameter space are the parameter space where personally I'm most excited about a discovery happening in the coming few years. So I now want to transition and tell you a little bit about how we can try to detect these particles. So I'm going to explain the other axis, which is going on in this plot. So the other axis is the axion-photon coupling. So I told you that axions couple to electromagnetism, and that turns out to be one of our best ways of going after actually detecting axions in nature. So what you're seeing here in solid colors are constraints that exist on this parameter space. The QCD axion, the one that solves the strong CP problem, lives in this orange space here. But you can have more general axion-like particles, which are also interesting, which live throughout the rest of this space. But the part we really want to get after is this part in orange. So you can see right here and up here are the only parts of the parameter space which have actually been probed experimentally. All of these lightly shaded regions are projections. So as I'll describe to you, the coming decade or so in this field is incredibly exciting because we don't know if this particle exists, but we will know in the coming years. All of the things which are in color are constraints that come from my group over the past few years. And I don't have time to explain most of them, but I will be focusing on this projection from DM radio, which is shown down here. So this brings me to the last part of this timeline, which is how can we detect these particles? So we're going to be using this coupling of the axion to electromagnetism. And as I mentioned, an axion wave can hit a magnetic field. And actually, most of the time, it just goes straight through. Because numerically, this coupling is very small, since it's inversely proportional to a very big number. But every once in a while, because of this interaction, the axion converts into an electromagnetic wave. And we can try to detect that electromagnetic wave. What are the properties of that electromagnetic wave? Well, I told you can think of the axion as dark matter, as a wave. But I can always think of a wave also as a collection of particles. Let's do that for a second. Let's think of this wave as a collection of non-relativistic particles whose energy is just set by the mass of those particles. So after they convert into electromagnetic particles, which are photons, and the energy of the photon is going to be equal to the energy of the axion by energy conservation. And the energy of the photon is related to the frequency of the photon. So if we combine all of these relations together, we can figure out that the frequency of the electromagnetic radiation is proportional to the axion mass times a bunch of fundamental constants. Then you can ask, given the masses I just told you about, where on the electromagnetic spectrum do these frequencies sit? And it just turns out that they sit in the radio and microwave range. So then you might say, great, you told me that there's dark matter surrounding the galaxy. So if axions are dark matter, I also know that there's magnetic fields in the galaxy. So maybe if I look with radio telescopes, I can start to see all of this beautiful structure emerging from the combination of axions with magnetic fields. And that's actually part of what I do in my group, a direction we've been pushing a lot over the past few years, is to look for axions using radio telescope data, in particular looking for neutron stars, because neutron stars have the strongest magnetic field out there in our universe. But I'm not going to be talking about this today. Instead, I'm going to be focusing on laboratory searches. But just to tell you, these searches are pushing down in sensitivity right here. They're the solid green ones. And our projected sensitivity for future telescopes extends down to cover this very exciting mass range here. The future of these radio searches for axions could definitely pick up a discovery. Let me mention these two experiments that you can see here, AVXMX and Haystack. These are essentially the only experiments to date which have actually reached sensitivity to the QCD axions. Let me tell you a little bit about how these work. We again convert our axions to electromagnetic radiation, but now in the laboratory with a laboratory magnetic field denoted here in orange. We get an electromagnetic wave and we match a cavity mode of a cavity to the frequency that that wave is going to have. And we can resonantly enhance that signal. But it turns out you can only resonantly enhance it so much. I told you the axion has an energy of its mass. That's not quite correct, because it does have some kinetic energy. Dark matter in our galaxy is moving at a few hundred kilometers per second. So the energy has kinetic corrections, which gives an energy dispersion on the order of the velocity of the dark matter in units of the speed of light squared, which is on the order of 10 to the minus 6, which tells you a quality factor of 10 to the 6 for your cavity is ideal. What size should the cavity have? Well, you want the wavelength to equal the size of the cavity. If you're going, for example, after 25 microeV in mass for the axion, that's a 5 centimeter cavity, which is great. That fits in your laboratory. This all seems to work. So that sort of reasoning has given the sensitivity from the ADMX, the limit from the ADMX experiment, the Haystack experiment, and these other ones too. As a theorist, I'm allowed to say this. This region will be covered by resonant cavity experiments in the coming years. It will take a lot of work, but it's already been done for some of the mass range, and it's just a matter of pushing this technology. But what about the rest of this mass range? If you start going up in mass, the cavity is too small, so it doesn't work. And if you start going down in mass, the cavity becomes too large, and again, it doesn't work. Because how are you going to build a 100-kilometer cavity? So there's a bit of a Goldilocks dilemma going on here. When we go outside of this mass range, we need new ideas. And I've been very motivated to think about this lower mass range because, again, this is where we expect the axion to live if it's connected with new physics associated with grand unification or string theory. And so I want to tell you a little bit about an idea that my collaborators and I came up with a while back now in 2016, which has turned into a sequence of experiments, which I'll quickly describe to you. Our original idea was called Abracadabra, stands for a broadband resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. Okay, so let's unpack this and understand how this experiment works. We're in the limit where the axion wavelength is much larger than the size of the experiment. So we want to write down Maxwell's equations in vacuum, except for the presence of axion dark matter. So you might recognize these equations, except for a few new terms, which involve my classical axion field, which you should just think of as an harmonic oscillator solution. So it's oscillating at the frequency of the axion mass with an amplitude, which is set by the requirement that the axion make up the dark matter. So it turns out I can neglect the gradient terms because the axion is moving very slowly, and the gradient terms bring down factors of the dark matter velocity, which is small relative to the speed of light. That only gives me this one new term. In the limit where the wavelength is much longer than the size of the experiment, I can make an approximation called the magneto-quasi-static approximation, which allows me to drop these two terms, with the caveat that my group has been looking at this recently, and we find actually in certain circumstances this is not a good approximation. But this is a detail which I'm happy to discuss afterwards if people are interested. Okay, but for now we just have this one modification to Maxwell's equation. We would have had del cross B equals 0. We have del cross B equals something which looks like an effective current. And it follows whatever magnetic field I put in the lab. So let's imagine I have a toroidal magnetic field in the laboratory. In the presence of axion dark matter, I induce an effective current density, which follows that magnetic field. And what do currents do? Just as the right-hand rule, it generates an induced magnetic field, which pierces the center of the toroid. And this field is going to be oscillating because the axion field is oscillating at the frequency set by its mass. So if I put in a pickup loop, as that magnetic field oscillates just by magnetic induction, I'm going to induce a current in that pickup loop, which I can try to detect with a current measuring device, maybe more sophisticated than that one shown here. In practice, we can put a resonator in this circuit, an LC resonator. So we just enhance by that same quality factor Q at the frequency corresponding to the axion. Of course, the problem is we don't know what mass that is. That's why simulations are helpful to help inform that mass, but at the moment it's wide open. So what we have to do is the same thing you do if you're driving down the road and you're trying to find a radio station and you don't know which one it is. You tune. You tune to a station, you listen, okay, it's not that. You tune, you listen, okay, it's not that. And we have to do this, and that makes the experiment much harder. There's actually a joke in this business that once we know the mass to axion, it essentially becomes an undergraduate level laboratory experiment. This experiment is so hard because we don't know the mass of the axion. We have to scan over millions and millions of different possibilities. So after we came out with that original theory paper, we convinced our experimental colleague, Lindley Winslow at MIT, to build this thing. Some of you might know Lindley because she was both an undergrad and a grad student here at Berkeley. So this is the experiment, and we've had a few results over the past few years. The experiment itself is 10 centimeters in diameter. It literally fits in the palm of my hand. It's a palm-sized dark matter detector. You can see the toroid that the wire is wrapping around here, which generate that toroidal magnetic field. Inside of it, superconducting shielding. And we have taken data and we found no evidence for axions, but in our most recent limits from last year, our sensitivity was limited by quantum noise within the readout, demonstrating that even though we can't detect new parameter space, the experiment is working as it is expected to. So what's next? We want to push down 8 orders of magnitude in coupling to the QCD axion. Luckily, we scale very well with the volume. So following Abracadabra, we formed a collaboration with our experimental colleagues down at SLAC and Stanford, and we're called the DM Radio Collaboration. And this includes us at Berkeley, both myself and Carl Van Bibber's group in nuclear engineering, and also Berkeley Lab. And this is our program. We're currently building a 50-liter experiment, which should do this thing in orange. We're designing a meter-cubed experiment, which should expand the sensitivity and actually cover the QCD axion over a non-trivial range of axion masses. And then I'll say our future aspirations are a multi-meter experiment, which would be able to look for axions at the scale of grand unification. So hopefully this program will cover a large chunk of the currently unprobed parameter space for axion dark matter. We're just one group in the game. So what I just described to you were these Abracadabra type experiments. I described to you the resonant cavity, AVXMX type experiments. You go to lower masses, there are other ideas, for example, Casper, which I can explain if people are interested. Going up to higher masses, you also need new ideas because the cavity is too small, but those ideas exist, except for perhaps some small gaps which need to be filled in where we're still looking for good ideas. Then at very high masses, astrophysical constraints play an important role. So the reason that the search for axions is exciting is currently this parameter space is open, but it's not going to be for much longer. And so if this is out there, we will find it. So thanks a lot. Yeah, it's a good question, actually. So our photons can't make up dark matter because they, well, for many reasons, which we can get into, but a very popular theory, which is closely related to this one, is that of the dark photon. And dark photons could have a sizable mass and behave essentially in every other way like our photon, except they would have a bigger mass. And these are dark matter candidates, which you can actually look for with very similar techniques to the ones that I described to you. So this dark matter radio experiment was a combination of two different groups. My group coming from Abracadabra and another group which was looking for these dark photons, and we decided to collaborate on an axion experiment. But yeah, that theory does exist. Yeah, good. So we expected, well, there's only one right answer for this QCD axion. So in that sense, yes, they're mutually exclusive. That's the game. So there is, if this axion exists, it has a mass, and that mass corresponds to an energy scale. And there's just a number for it. And so, you know, the crazy thing is we just have no idea what it is, except within these scenarios. So it could be 10 to the 16 GeV, or it could be 10 to the 10 GeV. Yeah, good. So maybe not. There are arguments you can make to suggest that maybe dark matter is half WIMPs, half axions. That sounds like it would be a very big coincidence, but maybe there are reasons that that coincidence happens. Maybe there are reasons that coincidence happens. Oh, good. So the question is it possible that dark matter could be some mixture of the various models that I showed? So for example, part WIMP, part axion. And the answer is yes. It could be. It could be part WIMP, part axion, part WIMP, part axion, part sterile neutrino, which is another thing which I described. Our visible sector is very complicated, and the dark sector could even be almost as complicated. We do have some constraints on how strongly dark matter can interact with itself, and we know it interacts relatively weakly with itself, but still within various parameters, the dark sector could be very complicated. Yeah, so for the QCD axion, the one which solves the strong CP problem, the answer appears to be no. And the reason is that, yeah, good. So right. So, but the reason is that that network disappears during the QCD phase transition. Because at the QCD phase transition, what happens is a part of the story I didn't have time to explain. The axion acquires a mass, and that mass gives tension to domain walls which form between the strings, and the whole network collapses and disintegrates into axion radiation. But people have talked about the possibility of axion-like particle strings, which could exist until much later and give observable signatures, for example, in the CMB. So if you have a world in which you have the QCD axion and related axion-like particles, those axion-like particle strings could last longer. Some of the signatures they could make, for example, would be polarization rotations, which you could see in the CMB. And so that's something which people do look for. Yeah, that's a great question. Okay, so the question is, why can't we say that CP is spontaneously broken and that theta equals 0 at the Lagrangian level? And you can. People try to build models this way. The reason it's hard is that we know that CP is not a symmetry of the standard model. There's CP violation in the standard model. There's CP violation in the same sector, in the strong sector through the quarks. And so it is hard to make CP a symmetry which is spontaneously broken, but then you preserve theta equals 0 below the scale of spontaneous symmetry breaking, or below that scale of symmetry breaking, but then you generate all of the other CP violation in the standard model. So normally attempts to do this invoke additional tuning. And the whole point of this is that we didn't want to tune things. So it is tricky. That doesn't mean that the universe couldn't be that way, but it's tricky. It gets harder when you try to write down that theory, when you try to actually write down the theory and you account for the other sectors. But this is, you know, if it's not the axion, that would be my bet that something like that is going on. So if we look for the axion and we don't find it, you know, those are going to be the models that everyone's going to be thinking about. Yeah. Yeah. So so what would it mean if DM radio found an ALP? So an ALP would be something which would live up here, for example. So not at this line. It would be very confusing. I don't know. It turns out that if there's an ALP here, it's very hard to have a QCD axion which lives nearby, because it would tend to, it would make it harder to solve that strong CP problem. It would generate some additional math kind of generically. So I really don't expect these experiments to find ALPs here. I would expect them to find ALPs down here. Sorry, ALP is an axion-like particle. So it's a particle which couples to electromagnetism, but doesn't couple to QCD. The mass is smaller, and so it would mean that there's less, it wouldn't conflict with the fact that we haven't seen a neutron electric dipole moment. So if the mass is really, really small for this axion-like particle, then it's perfectly fine to have many of them and to also have a QCD axion. If you make the mass bigger, it's harder to justify your QC axion solving the strong CP problem. So in my picture of the universe, my opinion for how things might play out is that there are a large number of axion-like particles, because these particles do appear relatively generically in the context of string theory, but they tend to appear with very small masses. One of them couples to QCD and becomes the QCD axion, but then you're left with n-1 of these things, which are down here. So if DM radio finds one up here, it would boggle my mind a little bit. Yeah. Yeah, look extra hard. Oh yeah, good. Yeah, so the way that Casper works is very different from the way that these other experiments work. It is not using the axion-photon coupling, but it's using the axion coupling to QCD itself. So what happens is the axion, it dynamically removes that neutron electric dipole moment. But if the axion is dark matter, it turns out the dark matter causes a residual oscillating neutron electric dipole moment. And so all of the neutrons would have in our galaxy, in our universe, would have a tiny oscillating electric dipole moment. And so Casper uses nuclear magnetic resonance techniques, just like your MRI machine, to try to look for that tiny oscillating neutron electric dipole moment. The frequency is set by the mass. So in this range, it's low radio frequency. It could be kilohertz to hertz. Yeah. So these are hard experiments. Casper is a very hard experiment, but yeah, that was the question that was asked earlier. So the question is, do the strings have any other phenomena other than creating the axions? And it actually appears no. The reason is that they disappear very early. So our earliest probe of the universe is the epoch of Big Bang nucleosynthesis. This is where protons and neutrons come together to form light elements. We can't see farther back, and this network has already disappeared by then. So if we ever get an earlier probe of our universe, then we might be able to see more direct evidence for them. But at present, the only thing we can do with them is predict the mass of the axion particle. Yeah.